This video will look at the idea and definition of electron volts. So, when working with particles, it can be convenient to use units of electron volts for energy. So I'm just going to make a note of that. So, when working and the electron volts symbol is little e, big V. And that will make more sense as we move through a description of what they physically are. Okay, so what is it? Well, 1 eV, so 1 electron volt, is the energy acquired by an electron. That's where our little e comes from, by an electron, by accelerating it through 1 volt of electric potential difference. Okay, so let's think about how this works. And I've already drawn out a parallel plate capacitor, which can provide us with an example of how this would happen. So what we're going to do is we're going to consider, so let's consider an electron. And first it's going to be at rest, and it's going to be near the negative plate. So consider an electron at rest near the negative plate of a parallel plate capacitor. Okay, so what's going on? Well, here's I'm going to draw the electron in orange. So we're going to have an electron, and we're going to put it, let's say right here. Okay. And just to remind ourselves, it is negatively charged. So we'll have a little negative sign there. And just to be really clear, we'll just say, hey, that's an electron. Okay, so we've got this electron. It's next to, we've placed it at the negative plate. And so there's going to be a force, an electric force, that is directed away from negative plate and towards the positive plate. So this is our F, let's say Fe. And so our initial velocity, we also know, is 0. Okay, so I've also noted that there's an electric field here, and there's also going to be a potential difference. So there's going to be a electric potential difference from one side to the other. Okay, And so what's going to happen next? Well, if we let the electron go, it's going to accelerate until it reaches the positive plate. And the amount that it's going to accelerate, well, that depends on the potential difference. So let's go take a look and work this through. So the electric field is going to do work on the electron. And the amount of that work is Q times our electric potential. So it's QV, and then more specifically, we know that the Q value is our fundamental charge, E. So notice that the work done is really little e V. And so that's going to be 1.6 times 10 to the negative 19 coulomb, our fundamental charge, times 1 volt, or 1 joule per coulomb. And so our work done is 1.6 times 10 to the negative 19 joules. And that's going to be equal to the change in energy. Because of our relationship between work and energy. So let's do a quick example to illustrate this. Really, I'm going to explicitly kind of note that this is little e, big V. Okay, so example. And to avoid getting too crowded, I'm going to bring this maybe down to the next page. So example. If an electron is accelerated through some example amount of potential difference, we could say some delta V is equal to 10 to the 7 volts. Then it gains how much energy? Well, since we know that the delta V is equal to 10 to the 7 volts, we also know that the energy it's going to get is 10 to the 7 electron volts. So that's 10 to the 7 EV. So that makes things really quick and easy, and that's one of the reasons that this unit is used for specific contexts. But let's take a look at its equivalency to what we're accustomed to, which is joules. And that will also further justify why in some contexts electron volts are used. So let's do that. So we're kind of going to do a check on this and also look at why. Well, the electric field can be equal to, well, we've got QV, energy. Got to keep the big E's straight. So energy is going to be equal to QV, and so we've already done that. But let's keep things in joules this time, right? So 1.6 times 10 to the negative 19 coulomb, because this is our charge on the electron, and then 10 to the 7 joules per coulomb. And so then we get an energy value that's 1.6 times 10. And even though this is, a big number for our potential, it's 1.6 times 10 to the negative 12 joules. So that's really, really small. So the electron volt unit really works in the context of particles, because otherwise we're dealing with all these really small factors. So 10 to the negative 12 type factors are smaller. Now, if we know that 1 eV is equal to 1.6 times 10 to the negative 19 joules, then the energy is equal to 1.6 times 10 to the negative 12 joules divided by 1.6 times 10 to the negative 19 joules per electron volt. And so we get back that the energy is 10 to the 7 electron volts. And so there's our example where we see the amount of energy from this situation can be expressed in electron volts or in joules, and electron volts gives us this really simple way to convert from one to the other. And if we ever need to go from electron volts back to joules, that's fairly straightforward as well, because we have this conversion. So that's electron volts.